It is our last lecture in Engineering 213, ladies and gentlemen. And as I said this week, we're just going to keep on trucking with our review problems. A couple of housekeeping items. And again, because it's our last class, I thought it would just be important to just make sure we're all formally aware of where things are on the grade standpoint. So, this is our grade in this class. Well, not my grade, y'all's grade. I'm going to get an A. That was a joke, not a funny one. Attendance. Attendance is up to date except for one day, which is today. We're going to take attendance. I'm going to post the attendance. That's the attendance grade in Engineering 213. I don't take attendance for the finals and whatnot. Homework. All the homework's graded. The only homework that's left is the bonus assignment. The university survey closes at midnight, okay? Of the 30 students in this class, 20 of them have done the survey. If, we got a 100% response rate on the university survey, I would just give everybody credit, but I had to have 100 response here because I don't know who did it. What I can tell you is 20 people have done the survey, but only 17 have uploaded proof. So if you've done the survey but you haven't uploaded proof to Blackboard, please do so. You're throwing away homework points without it. Again, you can say I'm a poopy head, that's fine, but do the survey and upload proof. It's free points. And if you do have any feedback for me or the class or anything to suggest moving forward, I really do appreciate it. Okay, I'm going to leave the Blackboard form open until Tuesday. So you only have till Friday or tonight to do the survey, but at the final, if anybody forgets to upload, you can have some time to do it. Okay, is everybody good? Any questions? And any general questions about the final? I think we've already discussed the logistics and what the final's going to be like, which is basically, it's formatted the same as all the other finals, it's just a tad longer. We have 2 remaining review problems today that I want to knock out for our week-long course review. Sound good? All right. And the code. Did everybody get it? Did you get the code? All right. I'll give you a sec. Did you get it? All right. Okay. So let's just jump right into our review problems. Okay. So this is problem number 4. We've already done the first 3. Any questions about the last 3 problems? So we had the particle statics problem, we had the centroid, but then between that we had the big old 3D cross product problem. Sound good? Okay, so with this problem, we have a truss. Okay, and I picked this truss because it's a pretty standard truss, but there is one result that is kind of interesting. So I just want to make sure that we're all on the same page. I have the truss here on the board as well. I want to make sure that we're clear on strategy. I did tell you to solve the truss using the method of joints with this problem, but let's just make sure that we understand our strategy. What is the first thing that we need to do in this problem? Reactions, exactly right. We've got to solve for the support reactions, okay, because we have to solve for every member, right? So we're going to need them, all right? And then the second part after that is the method of joints. Now, we're going to come back to this in terms of what is our order of solution, but for now, everybody should recognize that we need to solve for the reactions first. Okay, so let's talk about that. How many reactions do we have here at the roller? We have 1, which will be a vertical reaction. We'll assume it acts upward. We're going to call that AY. And then we're going to have a vertical reaction at C. We'll also assume that acts upward. Call that CY. But is there another reaction at C? There's a horizontal reaction. Which way do you think it's acting? In fact, well, let me just be more direct. Why did I draw it to the left over here? Because I have 48 kilonewtons going to the right. Okay? See, this has got to go to the left to balance that out. In fact, that probably motivates our first steps in the problem. So if we're solving for reactions, what do you think would be an easy one to do first? CX. And we would get that by doing what? Yeah, so we would be summing forces in the x direction. And we would say bless you. Okay. Or sorry, whoop. We would get that. Okay. And so, just so I don't have to scroll a bunch and just so we have a big picture, I'll try and repeat everything right here. Okay. So there's our first reaction. Now for our second reactions, or our second set of reactions, we have AY and CY. We can't apply the sum of forces in the, well, we could apply the sum of forces in the y direction, but it would give us two unknowns, right? Because all it would tell us is that AY plus CY has to equal what? 72, right? Because we've got 48 down and 24 down. So we ought to sum moments, okay? Now what I'm going to suggest is sum moments about a point that eliminates one of them. So that would be either A or C. And CX goes through both of them, so it doesn't really matter, okay? So I'm probably just going to sum moments about point A, okay? In fact, I think I kind of want to do that because I just want to make a point about moment summation. Let me move this up a little bit. Okay, so we'll sum moments about point A, okay? So how many forces are on the structure as a whole? We have 1, 2, 3, 4, 5, 6 forces, right? Let's just deal with them one at a time. Do we have to consider this horizontal 48 kilonewtons? The horizontal one at A, yes, we do. Because if I'm at A, here's the 48. That's going to rotate point A, right? So we have 48 kilonewtons times what moment arm? 3 meters. Does that generate positive or negative rotation according to our sign convention? Negative rotation. So we have negative 48 times 3. Okay? What about the vertical 48 kilonewtons? Do we need to consider that? No, because its line of action goes directly through it. So basically what we'll do is we'll say, okay, we had to consider this. We don't have to consider this. Do we have to consider AY? No. Do we have to consider the 24? Yes. Do we have to consider CY? What about CX? No. Because its line of action goes directly through A. So we only have 3 forces that we need to consider. This, and this. And that's kind of what we wanted because we wanted to isolate one of these reactions. So we're going to have 24 kilonewtons times what? 4 meters? Is that going to be positive or negative? Negative. Maybe what I'll do, let me move this down a little bit. And then we're going to have CY times what? I don't know why I drew those as exponents, but I'm just sort of going with it. All right, so we have 48 times 3. Let's see, 48 times 3, that's 120, and 44, that's 44, or 144. Minus 144. Minus 96 plus CY times 8 is 0. So that's going to be CY times 8 meters equals what? So 144 and 96, that's going to be what? 240? 240. And so we're going to get that, right? So this is going to be So there's that. So what's the last thing left to do? Solve for AY by summing forces in the Y direction. So what do we got? We've got AY going up, 24 going down, CY going up, 48 going down. So we'll say AY plus CY minus 24 minus 48. And so that's AY plus 30 minus 72. So that's going to be AY minus 42. And so, bam, bam, bam. And so this is 42. Okay. I want to be clear, this part right here, I actually want to take a second and take a breath. Is there any part about this that was confusing? Because we're going to do reactions again on the next problem. And in fact, reactions, the computation of support reactions, is one of the most ubiquitous topics in statics. So if you have a problem or there's something that you didn't understand here, this is the time to ask, okay? Because we are going to be doing this part quite a bit. Yes? So that's a great question, okay? The reason why is, okay, when we write the equation, so let's look over here. Okay, so when we write the equation, let's just add everything up. So we're going to add up a 48 kip load, which is positive, okay? And then a minus Cx, which is negative, okay? All right, but really what this turns into is the following equation. 48 minus x equals 0, right? I am proposing that in the system, we're treating it as negative. We write the equation as negative because it goes to the left. But then what I'm asking you is, what value of x satisfies this equation? 48, okay? So to answer the question about positives and negatives, we treat it as negative when we write the equation. But then once we write the equation, we then need to figure out what is the value that satisfies this equation. Does that make sense? And so sometimes what can happen is you write it as positive or negative in order to establish the equation, and then you solve for the variable and you get a negative answer. If you get a negative answer, what that means is you drew the arrow the wrong way to start with. That's what that means. That's a good question. Okay? That's good. And I want to make sure everybody else understands that too. Everybody good? This is good stuff, so don't hesitate if you got any questions. Okay. All right. So now what we need to do is we need to solve this structure using the method of joints. Okay? Now, let's look here at the board. So obviously, I'm going to start with joint B, right? That was a joke. Why would I not start my problem with joint B? There's too many unknowns. I cannot analyze a joint that has more than two unknowns. So I guess a question would be, give me a joint that we ought to start this problem with. Well, hold on. How many unknowns do we have going through D? 1, 2, 3. We have 3 members going through D. So we could start with joint C. What's another joint that we could start with? A, right? We can do joint C. We can do joint A. So what I'm going to do is say that we could start with C or A. And what I'm going to do is C first, then I'm going to do A. Okay? Now, I want to be clear that you could do either one in either order. It wouldn't matter. I'm doing C first and A because I have a point I want to make to you all. But it doesn't matter. You could do either one in either order. So let's do joint C first. Okay, and by the way, for this truss, the diagonals are all at a what, 3 to 4 slope ratio? All the diagonals are over 4 up 3, right? So all the diagonals are going to be, 5, 4, and 3. And the big thing to point out is the horizontal component is the bigger component, right? When we're dealing with the X and Y components, the horizontal component's bigger. Everybody okay with that? Okay. All right, so let's do joint C. So what do I do with joint C? The first thing I do is I draw the members. The next thing I do is I put my slope ratios down here. Okay. The next thing that I do is I list my reactions, which again, this is kind of why I wanted to put this here on the board so I wouldn't have to scroll up and down. I have 30 kilonewtons and I have 48 kilonewtons. Now, how many unknowns do I have now? Okay, so I've got this. Yes?
Is the slope ratio supposed to be 4?
Oh, you're right. Thank you. Thank you. So we're going to have 2 unknowns over here for the diagonal, 1 unknown here. Okay? So let's name these. So let's call this BC. Let's call this CEY, CEX. Okay? So let's just see if we can do this. All right, first off, okay, before I go down the rabbit hole, is everybody comfortable with this, bless you, with what I have here on the screen? Like, and able to construct this on your own, right? Notice a systematic process. Look at what I did. I started off with the members. This is joint C, member, member. Slope ratios, right? 3 and 4. Next thing I did, what are the loads that are already on the joint? Here and here. And then the next thing I did is my unknowns. This is a horizontal, this has 1, a diagonal has 2. That's it, okay? Is everybody okay with that? All right, so now let's do some figuring. Okay, so I have, how many horizontal unknowns? 2. How many vertical unknowns do I have?
1.
So let's just keep this real simple, okay? If I have, what is the vertical one got to be?
30.
30 going? Down. Okay? If that's 30, what's the horizontal?
Would that be 24 apiece?
What's that?
Would that be 24 apiece since this was
No. Whoa. Hold on. So, whenever you get the one component of a diagonal, you look at the other component of that diagonal and you ignore everything else. Okay? I'm looking at this diagonal member. This is 30, right? So I'm saying 30 is to 3 as what is to 4? 40. That's it. Okay? And it's got to be that way. Okay? The reason it's got to be that way is if I take the Pythagorean theorem of 30 and 40, it's going to go the same angle as the member. The resultant has to go the same angle, the same orientation as the member. Because truss elements, the forces are axial along the member. Whenever you get that first component of that diagonal, you ignore everything else and get the second component. Okay? And that's what we're doing. Okay. Now I want to make sure that part is crystal clear. Does everybody understand that? So if that's 40, and okay, so help me out. Now, how do I get this? Sum the forces in the x direction. So if I have 40 to the right and I have 48 to the left, what's this got to be? 8 to the right. Okay, I really want to make sure that is crystal clear. I want to make sure that that is understood. Is everybody okay with that? Is there anybody that doesn't understand? Anybody has any questions? So if that's the case, let's ask a couple things. So BC is 8 kilonewtons, and CE, how am I going to get CE? I'm going to use the Pythagorean theorem. When I use the Pythagorean theorem with 30 and 40, what am I going to get? 50. Now, can somebody tell me about the direction of these forces? Are they, when I say direction, I mean like tension or compression? Compression, which one? Both of them are compression, right? Because both of the sets of arrows, either this or both of these, are all facing toward the joint. Is everybody okay with that? Is everybody okay with the fact that when I got this one vertical, I immediately put that one to the left? That one down, that one to the left. Everybody okay with that? So this is compression, this is compression. So up here on my little diagram up here, that's what I'm going to do. All right, I want to take a breath and make sure we're all understanding what's going on, because I don't want to just barrel through this without y'all understanding it. Everybody good? Now, what was our plan? What do I do next? That was the plan, okay? This is important whenever you're doing these types of problems, is make sure you have a plan and go with it, okay? So now this is the joint that I said was going to have a weird, somewhat strange answer. Okay, so again, okay, everybody watch up here with me. So this is what I'm going to do. How many members do I have going through A? 2. I have a vertical and a horizontal. Do I have any diagonals? Do I have any loads that are applied directly to joint A? Exactly. I have a reaction of 42 kips. I am going to have an unknown in this member and an unknown in this member. So let's name them. Let's call this AD. Let's call this AB. Okay? Let's deal with the verticals first. So if I have 42 going up, what does AD have to be? Going down. So this is 42 going down. And by the way, if I were to make a conclusion about member AD, is it tension or compression? Because it's towards the joint. So this is 42 kilonewtons. In compression. But like I said, member AB is going to have a strange answer. Can somebody tell me what is the force inside member AB? Say it again. 0. There is no force inside member AB. What's happening is, so whenever you load a truss, what the truss does is it figures out how much force needs to go inside each member to maintain equilibrium. And what's happening with this particular truss is that there is no force necessary in this member to maintain equilibrium. That force doesn't carry, that member doesn't carry anything. Okay? And that the internal force inside this member is 0. Is that possible? Yes. Okay? How would we prevent that? Well, we just put the loads somewhere else. Like if we moved the loads to different configurations, different positions, we could probably develop a scenario where that didn't happen. But right now, with this configuration, with this truss, there is no force inside that member. Okay? I just want you to know that is possible. Okay? That is possible. Take CE312. We talk a whole lot more about it. Yes?
If DB, like the member DB was switched to AE, would that change that?
Wait, what?
Like if instead of running like.
You're talking about this member going like that?
Yeah.
Yeah, probably would. You're right. Another way would fix it, or another way that would change it is if we put a load right here, which we could do that. I mean, it wouldn't stop, nothing stopping us, but that would be one way of doing it. One way of doing it would be that. Another way would be doing that. You're 100% right. But I don't want to get into down the rabbit hole of like, what's the deal with zero force members and when they show up and when they don't. That's a CE312 question. But I just want you to know in here that it's possible. Does that make sense? Okay. I'm going to start knocking out the rest of this truss pretty quickly, if that's okay. What I'm going to suggest for moving forward is that we do joint E next. Now, why am I saying joint E? Well, joint E has 1, 2, 3 members, but we already know one of them, right? Okay. And then we're going to do joint B. And then afterwards, the truss is done. Okay. So I'm going to knock this out pretty quickly because I want to have some time for our final problem. So if we look at joint E, so joint E looks like this and that. Are there any external loads applied to joint E? No, it's just the joint. But here's the thing. We already know the force inside this member. Right? Because remember, this is a 4 to 3 member, and we got this. Where did I get this, by the way? Where did I get the 30 and 40? From joint C. We had already done joint C, right? Now, what I need to know is what direction do I draw the arrow? Which direction does the 30 kilonewton go? Up. Which direction does this go? Left. Why is it going up and to the left? It's going up and to the left because the member is in compression. Compressive forces face the joint. Okay? So, how do we deal with equilibrium? How many unknowns do we have? A vertical and a horizontal. Okay? So this is going to have a single vertical component, single horizontal. We're going to name these. Let's call that BE. Let's call this DE. What is BE going to be? $30 kilonewton down. What is DE going to be? It'll be 40. And it's going to go like that, right? Make sense? So that means that this is 40 in compression. This is 30 in tension. This is our first tensile member. There's a lot of compression members in this truss. But what's happening is a lot of the loads are sort of serving to push on the members. That's just what's happening. If we were to change the direction on some of these loads, it might change the answer. And then lastly, we have joint B. Okay? So as you start getting further along in the truss analysis, it becomes a bookkeeping problem more than it becomes anything else. Okay? So So there's the joint. Here's joint B, horizontal, horizontal, vertical, diagonal. Let's write the load that we know. Okay. Let's write the forces that we know. So this horizontal member here on the left, that's a zero force member. There's nothing going on in that member. Okay. This one is that, so that's 8 kilonewtons in compression. This vertical one is this, that's 30 kilonewtons in tension. And so the only thing we have left is this and this. Okay. So here's the cool part. Let's just handle each one separately. What's the horizontal component got to be? No, the horizontal. 8, because this is 8 this way, so it's going to be 8 that way. So this is 8. What about the vertical? 6, right? Which direction? Down, because there's 30 up, but there's only 24 down. So there needs to be another 6 going down. And by the way, what's the slope ratio on this member? 3 to 4, right? So does this 6 kilonewtons and 8 kilonewtons comport with this 3 to 4 slope ratio? Yes, it does, right? Because 3 is to 4 is 6 is to 8. Both values independently satisfy the slope ratio, and both values independently pointed the right way. So this is going to be BDY. Oh. And that's BDX. So BD. Yes. Now the question for you is, and for the class, is that tension or compression? Compression. And so I'm not going to redraw the truss on the screen here because I want to get to the next problem, but what's left in the problem? Is there anything left? Truss problem's done, right? We have every single member solved. And what joint did we not analyze? D. So if you wanted, you could do joint D as a check. Like you won't have to figure anything out, but you could analyze joint D and you would find that it balances. Okay. All right, I want to give a little bit of time for our next and final problem, but before I do, does anybody have any questions? Okay. I think if I had to pick, this last one was my favorite problem to develop for this whole exercise. Okay. So let's see if we can digest what's going on with this problem. So I have here a beam that is being shoved up against a wall and it's being held in place on the wall by an axial force of 40 kilonewtons, okay? And I'm giving you some coefficients of friction for the interaction between the wall and the beam. I want to determine the maximum load that the beam can support before motion starts to occur, and then I want to draw shear and moment diagrams. Okay. All right, so the big thing I want to point out is that the beam is not fixed over here at the right end. What's happening is, like this eraser is the beam, okay, and I've got this 40 kilonewton load here that is pushing the beam on the wall, okay? So what's happening here at the wall, okay? So if I take a 40 kilonewton load and it pushes against the wall right here, the wall's going to respond with a force like that, right? Now what do you think we ought to name that force? We could call it dx if you wanted, But I have a better name for that force. And I want to think about friction. I have a better name for that force. That's the normal force, right? This is the normal force that the wall is going to respond with, right? And so if I were to sum forces, that's that. Okay. Now, let's think about what's happening here. So, let's envision what's happening here. So, here's the wall pushing this against the wall, right? So I'm getting a normal force and response. And then I'm loading it this way, right? Now, if I'm loading it this way, the beam wants to slide down the wall, right? What's going to act against it? Friction, right? So what I'm getting at is I've got a vertical reaction right here. Now I could call that reaction dy, but I have a better name for that reaction. I'm going to call that reaction the resistive force, the frictional resistive force. That beam wants to slide down the wall, and that interaction between the beam and the wall is saying, I'm not going to let that happen. Okay? So I've got some friction trying to keep the beam up. Now, what did the problem say? The problem said figure out what the maximum loads need to be before the beam starts to move. So how do I figure out what the maximum friction force can be before the beam starts to move? I would say I need to figure out this. And how do I calculate the F sub m? Remember, F sub m for friction, that is the force at which motion occurs. How do I do that? Mu sub s times the normal force, the coefficient of static friction times the normal force, right? So what I'm saying is, under a normal force of 40 kilonewtons and a coefficient of static friction of 0.5, I have figured out what that reaction is. Does that make sense? If I push up against this beam and wall with a force of 40 kilonewtons and the coefficient of friction is 0.5, then it takes 20 kilonewtons before that beam starts moving, right? Does that make sense? Now, some of you are like, okay, but I don't see where the problem's going. Okay, let's go back to our free body diagram. Okay, so first off, we know that we can collapse this into a point load, that distributed load. We can collapse that into a point load. How much would the magnitude of that point load be? 20, right? Because it's 10 kilonewtons per meter for 2 meters. So that's 20 kilonewtons. And how far is that from A? Okay. Are there any reactions that I forgot to draw up here? There's a reaction at A, isn't there, right? Okay. So how many unknowns do I have left in this problem, by the way? Here, let me do this. Let me do this. How many unknowns do I have? Like looking at the free body diagram, what values do I not know? I don't know AY and I don't know P. How many equations of equilibrium do I have left? I've used one of them. 2. I have 2 unknowns and 2 equations. Maybe what I ought to do is just, I don't know, some moments at A, so what happens if I sum moments at A? Okay, let's go with this. Do I have to consider AY? Do I have to consider the 40 kilonewtons? Do I have to consider the distributed load? So I have a distributed load of 20, or the distributed load, I've idealized that as a 20 kilonewton load times a moment arm of what? 1 meter. Is that positive or negative? Negative. It's going to bug me if I don't do the same thing. I don't know why I'm doing that, but whatever. Okay, what about the P? Does the P generate moment at A? At a moment arm of? Four meters, right? From A, right? It's 4 meters, not 2. All right, what about the N? Does the N generate moment at A? Goes right through A. What about the FF? So we have a 40, which is going to be positive, times a moment arm of what? Oh, you're right, it's 20. That's going to equal 0, right? Does that make sense? What's my unknown? P. So, let's see. Let's see. That and that. I get the signs right? Yes, I did. So if I add the P over to the other side of the equal marks, I get 120 minus 20, or 100. I will have to call them back. Okay. And what did the problem say? The problem said figure out what load will cause motion to occur, right? Think about this. What would happen if P is like a little bit larger? If P is a little bit larger, then that means F sub F has to be a little bit larger to keep the beam in equilibrium. But that's not possible because that is the maximum amount of force that we can generate there before motion starts to occur. Does that make sense? We can't get any more. So that's the answer. Then what's left to do is to draw the shear and moment diagram. So I ask you, if I want to draw the shear and moment diagram, how do I do that? Well, what do I need to do? I need AY. I need to keep going. I need to get my other reaction. So I need to solve for the, I need to sum forces in the y direction. So I've got AY going up. I've got FF going up.
Are you counting the distributed load in this?
Oh, no, I am, yes. And then, so these are the forces going up. What's going down? I've got the 20 kilonewtons, and I've got P going down, right? That's what I've got going up. That's what I've got going down. The 20s are going to cancel, okay? And what am I going to get? AY minus P equals 0, so what's AY? 25 kilonewtons going up. So. Okay. Does that make sense? So, can I scroll up a little bit to give myself a little bit more space? So, if I were to redraw this beam, bless you. So, here's the beam. There's that. There's that. There's that. There's that. There's that. And then these are all 2 meters. Let me ask you a question. Do these 40 kilonewton loads matter at all on the shear moment diagram? No. The shear diagram is a change of vertical load. So these 40 kilonewtons, to be honest, we can kind of ignore them. So what does the shear diagram look like? And I'm going to do this really fast because we're running short on time. Okay, so what do? We start at 0, and then what do? We jump up to 25. And then what does the shear diagram look like from here to here? Diagonally down to a value of 5, right? Because that's a total of 20, right? No change. Drops down to minus 20. Brings back up to 0. Then we can do a little bit of integration. 20 times 2, this is going to be 40. So this right here is going to be minus 40. This part right here, that's going to be 5 times 2. That's going to be plus 10. And then over here, what we can do is we can say the average of 25 and 5 is 15. So 15 times 2 is 30, right? So this whole trapezoid area is going to be 30. And then when we construct the moment diagram, we're going to start at 0. We're going to jump up to 30. We're going to jump up to 40. Then we're going to jump back down to 0. Between these two regions here on the right, it's going to be linear. And then on the left, it's going to be a quadratic, and it's going to open downward. So we're going to do like that. Let me do I can do better than that. That, straight line, straight line. That's linear, linear. And this is quadratic. Whew, I did that kind of fast, I know. Does that make sense?
Sorry, real quick, when you go from the 25 to 5, why did you do that again?
How did I, okay, so the reason I did that is because, so it's a distributed load. So if it's a distributed load here, right, a constant load means a constant slope, right? So we drop down at a rate, so the slope of this line is minus 10 because the load is minus 10. So you drop, so, and remember how much load is that? 20, right? 10 times 2 is 20. So you go from 25 to 5 in a linear fashion.
Oh, okay.
Yeah. So yeah, so the slope of this line is 10 kilonewtons per meter, or negative, I should say, negative 10 kilonewtons per meter. Does that sound good? Any questions? All right, I'm going to pull up the code one more time, but I'll just say, guys, it's been a blast, everybody in class this semester. I will see you all on Tuesday.